What if everything you know about time, space, and reality is just an illusion? Imagine a universe where the past, present, and future coexist, and our existence is merely a projection. Join us as we explore groundbreaking discoveries that challenge the very fabric of the cosmos. We'll unravel the mysteries of time, delve into the secrets of life, speed, and rethink gravity's role in the universe. Interestingly, our journey to understanding time has been a tapestry woven through centuries of observation, philosophy, and scientific revolution. Ancient civilizations, such as the Egyptians and the Greeks, observed the cyclical patterns of the heavens. They saw time as a series of recurring events based on the rhythmic dance of celestial bodies, the sun, the moon, and the stars. For instance, the Egyptians divided the day into two 12-hour periods based on the shadow cast by the sun, and their intricate calendars were firmly rooted in their agricultural cycles. The Greeks, philosophers like Plato and Aristotle, pondered time as a constant, linear progression, a series of countless nows that march endlessly forward. For these early thinkers, time was more qualitative, woven deeply into the fabric of life and the seasons. Fast forward to the 17th century, and our understanding of time underwent a dramatic transformation with Isaac Newton's groundbreaking work in classical mechanics. Newton described time as an absolute entity, a steady, unchanging backdrop against which the events of the universe unfolded. This notion stood unchallenged until the dawn of the 20th century, when Albert Einstein introduced his theory of relativity, forever altering our perception of time. According to Einstein, time is not a constant, but is intertwined with the fabric of space itself, forming what we now call space-time. In his view, time can stretch and compress depending on the velocity at which an observer is moving, and the presence of massive objects like stars or planets can bend the space-time continuum. This revolutionary idea has not only deepened our understanding of the cosmos, but has also opened doors to exploring profound concepts like time dilation and the possibility of time travel, suggesting that time, once thought of as rigid and unyielding, is far more flexible and fluid than previously imagined. Imagine you and your best friend decide to take a trip. You stay on Earth, doing your usual activities, while your friend embarks on a high-speed adventure aboard a hypothetical spaceship that zips close to the speed of light. Let's give your friend a playful nickname. Say Speedy Sam. Now, while you're busy binge-watching your favorite shows and lounging around, Speedy Sam is jetting off at mind-boggling speeds, exploring distant corners of the galaxy. 1 year passes for you on Earth, but when Speedy Sam returns, you're amazed to discover that for them, only a few months have elapsed. This curious phenomenon is known as time dilation, a concept predicted by Albert Einstein's theory of relativity. It's as if Speedy Sam has a magic watch that runs slower compared to yours, simply because of the high velocity at which they traveled. This effect is not just science fiction. It's actually been observed with precise atomic clocks on airplanes and satellites, which tick slightly slower compared to those on Earth. Visualize this. You're like a leisurely snail ambling along and experiencing time normally. Meanwhile, Speedy Sam, the superfast jet setter, is like a blur of motion, zipping by and experiencing time more slowly. This mind-bending aspect of physics shows that time, something we often think of as steady and universal, can stretch and compress depending on how fast we're moving. So, next time you and Speedy Sam plan a trip, remember, the faster you go, the slower you age, or at least that's how it would seem from the perspective of us earthbound snails. When scientists refer to time as an illusion, they are delving into one of the most intriguing and abstract concepts in physics and philosophy. This idea suggests that our everyday experience of time, past, present, and future, might not reflect the true nature of reality. Nothing. It's a word we use daily, yet its true meaning eludes us. What exactly is nothing? Can it exist? And if it can, what is it made of? Join us today as we prepare to have your understanding of everything and nothing transformed. Nothing, in a scientific context, is often defined as the absence of matter or the complete lack of anything that possesses mass or volume. This concept can be more complex than it appears, particularly in fields like cosmology and quantum physics. In everyday terms, we might think of nothing as an empty space, but scientists have discovered that what we perceive as empty space still has properties and behaviors that defy our intuitive understanding. One intriguing aspect of this definition comes from quantum physics, where it is suggested that even in a vacuum, which we might consider nothing, there are still fluctuations in virtual particles popping in and out of existence. This means that true nothingness may never be fully realized. There are always underlying fields and energy exchanges occurring at the quantum level. This revelation challenges our traditional conceptions of emptiness. Cosmologically, the idea of nothing extends to the universe itself. The Big Bang theory posits that everything we see today originated from a singular point, often described as a state of nothingness. However, this nothing was not simply empty, but a densely packed point with high energy, eventually leading to the expansion of the universe. The nuances of nothingness raise profound questions about the origins of existence. Moreover, discussions about nothing intersect with philosophical inquiries, contemplating whether true nothingness can exist. These explorations bridge science and philosophy, illustrating that the more we investigate nothing, the more we realize it is woven with complexity. The sheer richness of this concept highlights the limits of our understanding, inviting us to ponder the very foundations of reality. Physicists differentiate between empty space and true nothingness by examining the properties and characteristics associated with each. Empty space, often referred to as a vacuum, appears devoid of matter, yet it is laden with fundamental forces, energy fluctuations, and even virtual particles that momentarily emerge and vanish. This means that what we perceive as a void is far from lifeless. It is a dynamical arena where quantum events occur, influencing the behavior of matter and energy around us. Contrastingly, true nothingness would imply a complete absence of everything. No matter, no energy, no forces, and no space-time, time itself. In current scientific understanding, such a state is elusive and possibly non-existent. The very fabric of our universe is interwoven with a complex framework of quantum fields, suggesting that the concept of absolute nothing is more philosophical than physical. Even the most expansive vacuums still adhere to laws of physics, retaining properties such as gravitational influence and energy. Additionally, physicists utilize devices like particle accelerators to probe the nature of empty space. When particles collide at high energies, they can create ephemeral particles from a vacuum, showcasing that even what appears to be empty is rich in energy and capable of producing matter under the right conditions. This phenomenon reinforces the idea that empty space is teeming with potential, contrasting sharply with the idea of true nothingness, where such activity will be impossible. The distinctions become even more profound in the context of cosmology. When contemplating the universe's origins, scientists argue that the Big Bang did not emerge from nothing in the true sense, but rather from an extremely hot and dense state that could be misinterpreted as nothingness. Thus, the boundaries between empty space and true nothingness lie not only in observable properties, but also in deeper theoretical implications, making the exploration of these concepts a fascinating journey into the cosmos. The concept of absolute nothing existing within our universe poses profound questions that touch on both physics and philosophy. In the context of our universe, absolute nothingness would mean a complete absence of matter, energy, space, and time. However, current understanding suggests that such a state may not be possible within the framework of quantum mechanics and cosmology. According to quantum field theory, even what we consider to be a perfect vacuum is not completely empty. Instead, it is filled with quantum fields that result in persistent fluctuations. These fluctuations give rise to virtual particles that transiently emerge from a vacuum, indicating that empty space is, in fact, an active participant in the dynamics of the universe. This phenomenon suggests that even if matter were to be removed, the underlying quantum fields would still exist, preventing true nothingness from arising. In cosmology, the origins of our universe are attributed to the Big Bang, which originated from an extremely hot and dense state. This implies that before this event, the concept of absolute nothingness may not have applied. Rather than emerging from nothing, the universe's inception involved various forms of energy and fundamental particles compressed into a single point. Therefore, the existence of any state resembling absolute nothingness seems incompatible with the known principles of physics governing the universe. Furthermore, the philosophical implications of absolute nothingness raise additional challenges. If true nothingness were to exist, it would lack the basic elements necessary for observation or interaction, making it nearly impossible to conceptualize within the scientific framework. Thus, while it is fascinating to ponder, our current understanding suggests that absolute nothingness is an abstract idea rather than a realizable state within the universe we inhabit. This exploration invites continual inquiry into the nature of existence and the structures that form the reality we experience. The concept of nothingness has undergone significant evolution throughout scientific history, reflecting deeper understandings of the universe and our place within it. In ancient philosophy, thinkers like Aristotle grapple with the notion of nothing as an idea of absence. He famously rejected the idea of a void, positing that nature abhors a vacuum and that something cannot come from nothing. Such views dominated for centuries, shaping early scientific and philosophical thought. As science progressed, particularly during the Enlightenment and the emergence of modern physics, the understanding of nothingness began to shift. Isaac Newton's laws of motion and universal gravitation suggested a universe filled with matter and forces, reinforcing the notion of a tangible, filled space. However, Newton's universe also opened the door to considering what lay beyond observable matter, although pure emptiness was still not thoroughly explored. The advent of quantum mechanics in the early 20th century brought revolutionary changes to the concept of nothingness. With the discovery of quantum fluctuations, scientists found that even empty space is alive with activity. The vacuum state, once thought to be devoid of anything, is understood to contain fluctuating energy levels and virtual particles. This realization fundamentally altered the view of nothingness. No longer could it be considered simply as an absence, but rather as a dynamic entity with its own properties. In contemporary cosmology, the understanding of nothingness has further matured through insights gained from the Big Bang Theory. Here, the early universe is viewed not as an empty void, but as an extraordinarily dense and hot singularity brimming with potential. Recent theories about dark energy and the structure of space-time continue to challenge and refine the definition of nothingness. The evolution of this concept reflects a continual quest for knowledge about the universe, revealing that nothingness is intricately tied to existence and the very laws of physics defining our reality. The concept of zero plays a crucial role in understanding nothingness, particularly in mathematics and physics. At its core, zero represents the absence of quantity, the point at which there is nothing to count. This foundational idea allows scientists and mathematicians to express the concept of nothingness in a way that can be systematically analyzed and manipulated. In doing so, zero becomes a powerful tool for delineating absence from presence, bridging the gap between concepts that might seem purely philosophical and those that are rigorously scientific. In mathematics, zero is not merely a placeholder. It is an essential element in arithmetic and algebra. It facilitates operations that involve the idea of nothingness, enabling equations to express balance and equivalence. For example, in the equation representing equilibrium, the left and right sides may sum to zero, demonstrating how zero can signify a state of rest. By offering a numerical representation of nothingness, zero allows for clearer definitions and explorations of existence itself. Within physics, zero takes on even more profound implications when describing states of energy, temperature, or movement. A value of zero can often indicate a lack of activity or presence. For instance, absolute zero refers to a theoretical state in which molecular motion ceases entirely. Such concepts highlight how zero helps us recognize boundaries between states of being and non-being, shaping our understanding of the universe's laws and behaviors. Moreover, as discussions around quantum mechanics have revealed, even in a vacuum state where nothing seems to exist, the number of particles or energy can still fluctuate around zero. Thus, the interplay of zero and nothingness serves as a reminder that absence itself is inherently tied to presence. The concept of zero thus underscores the intricate relationship between nothingness and existence, demonstrating that even the absence of something carries substantial meaning in scientific inquiry. Different cultures have varied perspectives on the concept of nothingness, often shaped by their philosophical, spiritual, and scientific traditions. In Eastern philosophies, such as Buddhism, nothingness is often associated with the concept of emptiness, or sunyata. This idea denotes not just the absence of being, but rather a deeper understanding of the interconnectedness of all things and the impermanence of existence. Emptiness, in this context, is not something to be feared. Instead, it is seen as an opportunity for enlightenment and realizing the true nature of reality when notions of self and identity dissolve. In contrast, ancient Greek philosophy approached nothingness more with skepticism. Thinkers like Parmenides questioned the very notion of nothingness, asserting that nothing comes from nothing. For them, being was a primary reality, and any conception of nothingness was often viewed as a paradox or an idea that could lead to confusion. This skepticism carried over into later Western philosophies, when nothingness was often grappling with ideas of existence and non-existence. The discussions around the void and existentialism, especially in the works of philosophers like Jean-Paul Sartre, highlighted the existential dread associated with nothingness and the search for meaning within it. Indigenous cultures have unique interpretations of emptiness and nothingness, often integrating these concepts into their cosmologies. Many Native American philosophies, for instance, express a harmonious relationship with nature, wherein the absence of material possessions or the emptiness found in nature is viewed positively. Emptiness can signify a space of potential creation and regeneration, emphasizing the cycle of life rather than a finality of absence. In contemporary thought, particularly in the field of art, literature, and psychology, nothingness is often explored as a thematic element, representing aspects of hope, despair, or potential. Whether depicted in literature's exploration of existential themes or in ART's abstract representations, the cultural perception of nothingness continues to evolve. This reveals a rich tapestry of interpretations that reflect the values, existential attitudes, and spiritual beliefs of various societies, highlighting that the quest to understand nothingness is as diverse as humanity itself. The quantum vacuum is a fundamental concept within quantum field theory, often described as the lowest energy state of a field where no particles are present. However, this understanding can be quite misleading if we equate the quantum vacuum with the notion of nothingness. Although it may appear empty, the quantum vacuum is anything but devoid of activity. It teems with dynamic fluctuations and a myriad of virtual particles that pop in and out of existence, giving rise to a constantly changing backdrop of energy. These quantum fluctuations challenge the traditional idea of nothingness. In a classical sense, nothing might be thought of as an absolute void, but the quantum vacuum reveals that even this emptiness is profoundly rich. The vacuum has intrinsic properties, such as vacuum energy, which can influence physical phenomena. For example, the Casimir effect demonstrates how vacuum fluctuations can lead to observable forces between objects placed very close together, essentially proving that empty space is loaded with energy. The relationship between the quantum vacuum and nothingness also emerges in discussions about the origins of the universe. Many cosmological models posit that the universe originated from a state associated with vacuum energy. While the quantum vacuum might be void of matter, its energy content suggests a potential for creation and change, prompting consideration of whether true nothingness could ever exist. In this light, the quantum vacuum implies that the very concept of nothingness may be more nuanced and complex than simply the lack of anything substantial. Thus, rather than serving as true nothingness, the quantum vacuum underscores the idea that what we perceive as absence is a vibrant state full of dynamic possibilities. The discoveries of quantum mechanics highlight how our understanding of nothingness is evolving, demonstrating that even the emptiest of spaces contains the seeds of existence. The exploration of the quantum vacuum continues to redefine our perception of reality, blurring the lines between being and non-being. Virtual particles represent a significant challenge to our traditional understanding of empty space by demonstrating that what we perceive as a void is actually a seething mass of activity at the quantum level. According to quantum field theory, virtual particles are temporary fluctuations that occur in the quantum vacuum, emerging and disappearing in incredibly short time frames. These particles are never directly observable, yet their effects can be measured, proving that empty space is not static or devoid of substance. The existence of virtual particles fundamentally alters our conception of empty space. Instead of being a lifeless vacuum, it is more accurately described as a dynamic arena where energy fluctuations occur continuously. These fluctuations allow virtual particles to act as messengers of forces, influencing interactions between real particles. For example, in quantum electrodynamics, virtual particles facilitate electromagnetic interactions by mediating forces between charged particles like electrons. This showcases that empty space is rich with potential, wherein interactions are constantly occurring, even if they remain hidden from direct observation. One of the most striking implications of virtual particles is the Casimir effect, which illustrates how two uncharged parallel plates can experience an attractive force due to the restriction of virtual particles between them. This phenomenon serves as empirical evidence that empty space can exert real forces and influence physical objects, providing tangible proof that our understanding of vacuum as a mere absence of matter is incomplete. Moreover, the concept of virtual particles also invites us to rethink fundamental questions about the nature of reality. They challenge the notion that existence strictly relies on observable entities by revealing that much of the universe's behavior cares beyond traditional measurements. Virtual particles highlight the incredible complexity of quantum mechanics and emphasize that empty space is fundamentally interconnected with the workings of the universe, reshaping our understanding of both space and the fabric of reality itself. The Casimir effect is significant in relation to nothingness because it provides tangible evidence that what we perceive as empty space is far from being an absolute void. Discovered in the mid-20th century by physicist Hendrik Casimir, this phenomenon occurs when two uncharged parallel plates are placed very close together in a vacuum. Surprisingly, these plates experience an attractive force that pulls them toward each other, a result of the fluctuations of virtual particles in the quantum vacuum. This effect illustrates that even in what we define as emptiness, there is a vast energy field at play. The vacuum between the plates restricts the types of virtual particles that can exist, leading to a difference in energy density on either side of the plates. Consequently, the energy from a quantum vacuum pushes them together, revealing that empty space has properties and behaviors that challenge our conventional understanding of nothingness. The Casimir effect shows that nothing is not inert or passive. Instead, it is filled with the potential for interactions that can have observable consequences. Furthermore, the Casimir effect has implications for theoretical physics that extend beyond a simple understanding of nothingness. It highlights the inherent complexities of the quantum vacuum and urges scientists to reconsider the dynamics of space itself. This realization expands the definition of nothingness from an absolute absence to a realm of possibilities where fluctuations and virtual entities can produce measurable effects. In a broader philosophical context, the significance of the Casimir effect invites reflection on the nature of existence itself. It compels us to recognize that even in our most profound contemplations of nothingness, we uncover layers of complexity and activity. Thus, the Casimir effect serves as a striking reminder that the universe operates in ways that often defy our intuitions, urging us to reconsider the boundaries between existence and non-existence. The presence of dark energy profoundly impacts our understanding of empty space by introducing a dynamic form of energy that permeates throughout the universe. Discovered through observations of the accelerated expansion of the universe, dark energy comprises about 70% of the universe's total energy content. Contrary to our traditional notion of empty space as a mere void, dark energy suggests that it is an active participant in the cosmic landscape, contributing to the overall behavior of the universe and its expansion. One of the most intriguing aspects of dark energy is that it appears to exert a repulsive force, working against the attractive pull of gravity. This imbalance accelerates the expansion of the universe, which challenges earlier models that depicted a static or gradually slowing cosmos. As it stands, dark energy offers a mechanism by which seemingly empty space can foster rapid cosmic growth. Instead of being a passive void, empty space is revealed as a complicated mixture of energetic properties that influence the fabric of the universe. Additionally, dark energy's influence on empty space raises important questions about the nature of the vacuum itself. In the context of quantum field theory and the quantum vacuum, understanding dark energy reveals potential connections between vacuum energy and the observed acceleration of cosmic expansion. While quantum fluctuations characterize empty space, dark energy introduces an inherent energy density that affects the universe on large scales, indicating that our perception of nothingness must incorporate these active forces. This evolving understanding of empty space, shaped by the presence of dark energy, challenges us to rethink foundational concepts in cosmology. Rather than regarding the universe as a static stage on which events unfold, we see that space itself is dynamic and constantly influenced by forces we are only beginning to comprehend. The interplay between dark energy and empty space illuminates the deeper complexities of the universe, inviting ongoing inquiry into both the nature of existence and the fabric of reality itself. Attempting to visualize or conceptualize true nothingness is inherently challenging, as our minds are conditioned to think in terms of existence and tangible experiences. One approach is to consider nothingness as a fundamental absence, a complete lack of matter, energy, space, and time. However, this definition can quickly become abstract and elude our understanding, as even the absence of anything can still evoke questions about how we perceive reality. One way to approach this visualization is through analogy and abstraction. Imagine a perfect void, an emptiness without light, sound, or any form of physical presence. This can be akin to the concept of absolute darkness, where even the faintest glimmer of light or color is absent. In this state, our usual sensory perceptions fail to apply, leading us to confront a conceptual space devoid of any characteristics we typically associate with being. Philosophical explorations also play a vital role in comprehending nothingness. Thinkers like Martin Heidegger and Jean-Paul Sartre examine the existential implications of nothingness, often illustrating how it relates to human experience. In these discussions, nothingness might be linked to ideas of emptiness in existence or the void that arises in moments of profound reflection. Such concepts hint at nothingness as profound state rather than a mere absence, suggesting that, paradoxically, it can illuminate our understanding of what it means to exist. Additionally, visualizing nothingness can involve contemplating the boundaries of our universe. The observable universe has limitations, and when we think about what exists beyond these boundaries, we encounter the idea of incomprehensible emptiness. However, even this conceptualization remains intertwined with our ideas of space, time, and energy. Ultimately, engaging with true nothingness leads to the recognition that our cognitive frameworks are deeply rooted in the phenomena of existence, making absolute nothingness a conceptual challenge that invites us to explore the unknown. Engaging in mental exercises can help to approach the difficult concept of absolute void by promoting abstract thinking and challenging our conventional perceptions of existence. One effective exercise is a thought experiment of emptying the mind. This involves finding a quiet space and practicing meditation or mindfulness to consciously let go of sensory input and internal dialogue. By allowing thoughts to fade and focusing purely on a state of mental silence, participants can begin to sense a level of emptiness that may mirror the characteristics of an absolute void. Another exercise is visualizing layers of existence. Start by imagining the physical elements surrounding you, including objects, people, and the environment. Gradually, strip away these layers, picturing each element disappearing one by one. First the people, then the objects, and finally, the familiar sounds. As you continue this exercise, strive to reach a point where you perceive a vast emptiness. Rather than feeling distress, this visualization can foster a sense of openness to the idea of an unfilled space, inviting reflections on the nature of absence. Additionally, engaging with paradox can be another useful exercise. Consider the idea that defining something as nothing inherently requires the use of language and thought, which are tools grounded in existence. Ponder how an empathetic acknowledgement of nothingness resides within the context of being. By grappling with these contradictions, the mind can cultivate a deeper understanding of the intricate relationship between existence and non-existence. Lastly, consider reading and reflecting on philosophical texts that approach the notion of void or nothingness. Engaging with the writings of thinkers like Martin Heidegger, Jean-Paul Sartre, or Eastern philosophies such as Buddhism can provoke thought and invite exploration into these complex themes. This intellectual exercise encourages the individual to confront and process the abstract attributes of the concept while grappling with profound existential questions. These combined mental exercises create a pathway to approaching absolute void, expanding the mind's capacity to engage with the challenging yet intriguing notion of nothingness. Comprehending complete nothingness is challenging for the human mind due to several factors rooted in our cognitive and sensory experiences. First and foremost, our perceptions are fundamentally anchored in the existence of things. We are creatures of experience, constantly interacting with a world filled with matter, energy, and sensory input. From childhood, we learn to understand the world through these interactions, making it difficult to conceptualize a state devoid of all forms of existence. Our brains are wired to recognize and categorize what is around us, meaning that the idea of nothingness, a complete absence, poses a significant cognitive challenge. Additionally, language plays a crucial role in shaping our thoughts. Most languages are built upon concept of existence, utilizing words that describe objects, sensations, and experiences. Attempting to articulate or define nothingness often leads to paradoxes, as we find ourselves using terms that inherently relate to something instead of nothing. This linguistic limitation creates a barrier when trying to fully embrace the concept of absolute void, leading to confusion and inconsistency in our understanding. Philosophical inquiries also complicate our relationship with nothingness. Many philosophical traditions explore the nature of existence and non-existence, often arriving at profound questions without clear answers. This exploration confronts individuals with existential dilemmas about meaning, purpose, and the nature of reality, which can be both thought-provoking and unsettling. When faced with the idea of complete nothingness, the mind inherently grapples with deeply rooted fears and uncertainties about the implications of such a state. Finally, the notion of nothingness tends to evoke a sense of existential dread. Confronting the idea that there could be a state completely devoid of life, purpose, or structure invites anxiety and confrontation with our own mortality. This emotional response can further inhibit our ability to engage with the concept intellectually. The combination of these cognitive, linguistic, philosophical, and emotional factors results in a multifaceted challenge for the human mind when it comes to comprehending complete nothingness. Sensory deprivation experiments provide a fascinating lens through which to explore the experience of nothingness, as they specifically aim to isolate individuals from external stimuli. In these experiments, participants are placed in controlled environments, such as flotation tanks or dark, soundproof rooms, where visual and auditory inputs are significantly reduced or eliminated. This environment encourages introspection and alters the participant perception of reality, often leading to experiences that resonate deeply with the concept of nothingness. As external stimuli diminish, individuals often report heightened awareness of their internal thoughts, emotions, and sensations. The absence of sensory input creates a unique state where the usual distractions of daily life fade away, allowing participants to confront their own minds. This isolation can evoke feelings of profound emptiness, or conversely, an overwhelming flood of thoughts and emotions. Some individuals describe this experience as unsettling, while others may find it liberating, highlighting the diverse interpretations of what nothingness can mean when stripped of external influences. Moreover, sensory deprivation can lead to altered states of consciousness, where time perception, self-identity, and reality often seem to blur. Participants may experience states of deep relaxation, dissociation, or even hallucinations. These phenomena can challenge conventional perceptions of existence and non-existence, as the awareness of one's own consciousness persists even in the absence of external stimuli. In this sense, the experiments serve to illustrate that nothingness is not simply a void, but a complex state that exists alongside consciousness itself. Ultimately, sensory deprivation experiments illuminate the intricate relationship between perception and the concept of nothingness. They demonstrate that the experience of emptiness can evoke a spectrum of emotional and cognitive responses, pushing individuals to confront what it means to exist in the absence of external influences. Through these explorations, participants gain insight into the nature of reality, presence, and the human experience, enriching our understanding of nothingness beyond mere abstraction. Consciousness profoundly shapes our understanding of nothingness. When we confront the concept of nothingness, it is our consciousness that allows us to recognize the absence of things rather than an empty void that lacks any definition at all. This awareness is essential. Without consciousness, we would have no insight into anything, whether that be the presence of objects or the very notion of emptiness itself. Our minds are constantly interpreting sensory information and constructing a reality filled with meanings and sensations. When we think about nothingness, we are tapping into a state defined by the lack of these interpretations. This mental engagement occurs because consciousness enables us to question and reflect on our experiences. We can contemplate a scenario without matter or form, even though such a state is difficult to grasp and perhaps beyond our typical experiences. It is through the lens of consciousness that we can explore and examine the boundaries of existence, framing our understanding in ways that provoke curiosity and deeper philosophical inquiries. Interestingly, concepts of nothingness extend into the realms of physics and cosmology as well. For example, scientists explore the vacuum of space, which is often misperceived as simply empty. In reality, even the emptiest regions of space teem with quantum fluctuations, suggesting potential energy. Consciousness allows us to navigate complex theories that challenge our perceptions and broaden our understanding of reality beyond everyday experiences. The interplay between consciousness and nothingness ignites discussions in both scientific and philosophical realms. The ability to conceptualize nothingness illustrates our unique capability to ponder existence itself. Thus, while we may grapple with what nothingness truly entails, it is our conscious experience that grants us the tools to engage with these profound questions, enriching our appreciation of the universe and our place within it. Artists and creators tackle the concept of nothingness in various innovative ways, using their mediums to provoke thought and evoke feelings that relate to absence or void. In visual art, for example, artists often utilize blank canvases or vast empty spaces to symbolize nothingness. This minimalist approach can challenge viewers to confront their thoughts and feelings about emptiness, inviting them to fill a void with their interpretations and emotions. The choice of color, or sometimes a complete lack of it, becomes a powerful statement on absence and the spaces between existence. In literature, themes of nothingness often manifest in existential narratives where characters grapple with the meaning of life, identity, and the void in between experiences. Authors use language to explore feelings of alienation and desolation, crafting passages that emphasize what is absent. This exploration invites readers to reflect on their own experiences of nothingness, encouraging an introspective journey through the characters' dilemmas and the philosophical questions they pose. The narrative can serve as a mirror, reflecting our own encounters with absence and the search for meaning in a world that often feels hollow. In music, the representation of nothingness can take on an auditory form. Composers might use silence, pauses, or sparse instrumentation to create a sense of emptiness or void. By weaving silence into their compositions, they allow listeners to experience the space between notes, transforming absence into a poignant part of the piece. This engagement with silence creates profound contrast of sound, highlighting feelings of isolation or contemplation, further deepening the listener's emotional connection to the concept of nothingness. The interpretations of nothingness in art, literature, and music often connect on a deeper level, transcending traditional boundaries and inviting audiences to explore the complexities of existence. By grappling with nothingness, creators challenge us to confront uncomfortable truths and develop a richer understanding of the human experience, encouraging meaningful reflections on our own lives and the spaces that define them. Mathematics offers intriguing framework for examining the concept of nothingness, providing tools that can enhance our understanding of absence and void. One compelling notion is the concept of zero, which in mathematics represents a state of having no quantity. Zero serves as a foundation for numerous mathematical operations, acting not just as a placeholder but as a pivotal point in various equations. It allows us to explore the transitions between existence and non-existence, illustrating how something can be derived from nothing. In the realm of set theory, the idea of the empty set is another significant mathematical representation of nothingness. The empty set contains no elements, yet it is still acknowledged as a fundamental concept that facilitates discussions about collections and operations within mathematics. This abstraction helps illustrate how nothingness can still hold value and meaning within a mathematical context, emphasizing that even in absence, there is a framework for understanding. Beyond pure mathematics, concepts like fractals demonstrate how complexity can arise from seemingly empty spaces. When examining fractals, one finds infinite patterns emerging from simple geometric principles. This reinforces the idea that nothingness can give rise to infinite possibilities, suggesting that within the void, there exist hidden structures and potentialities waiting to be revealed. Such insights prompt deeper philosophical inquiries into the nature of existence and the cosmos. In physics, theories involving vacuums and quantum mechanics further intertwine with mathematical principles. The vacuum of space is not truly nothing, but instead a dynamic field bursting with activity at the quantum level. Here, mathematical tools allow scientists to describe behaviors of particles and energy that challenge traditional notions of emptiness. By utilizing mathematics, we can better navigate the complexities of nothingness, transforming from an abstract concept into a subject of real scientific inquiry, ultimately enriching our comprehension of the universe and our place within it. The relationship between nothingness and the philosophical concept of non-existence is profound and complex, often serving as a focal point for deep existential inquiry. Nothingness typically refers to a state or condition devoid of any existing entities, while non-existence leans more toward the idea of something that does not exist or has never existed. This distinction invites philosophical exploration into the nature of reality and the very fabric of existence itself. One significant philosophical approach to nothingness is rooted in existentialism, where thinkers like Jean-Paul Sartre and Martin Heidegger contemplate the implications of nothingness on human awareness and existence. For these philosophers, nothingness is intertwined with freedom and choice. It represents an absence that allows consciousness to question its own significance. This exploration suggests that understanding nothingness can lead individuals to confront the ultimate questions of purpose and meaning as they recognize their existence amid a potentially indifferent universe. Additionally, the philosophical inquiry into non-existence often grapples with ideas about what it means for something to not be. If we consider the concept of non-existence, we must reflect on whether it is possible to fully comprehend something that has never been present. This raises questions about the nature of absence. Does non-existence have any properties, or is it a state that utterly resists comprehension? Philosophy addresses these questions by pushing boundaries, challenging our established notions of reality, perception, and the cosmos. The ideas of nothingness and non-existence are not only abstract concepts, but also provoke fundamental questions about life, our place in the universe, and the parameters of reality. This contemplation is important as it shapes not just philosophical thought, but also influences artistic expression and scientific inquiry. By deeply engaging with nothingness and non-existence, we gain insight into the multifaceted nature of existence itself, prompting us to explore the very essence of being and the void that surrounds it. Dreams and meditative states offer unique insights into the experience of nothingness, allowing individuals glimpses of a reality that transcends ordinary perception. When we dream, especially in the realm of lucid or profound dreams, we can encounter states where familiar boundaries dissolve. The surreal quality of dreams often removes the constraints of time, space, and logic, confronting us with experiences that might feel like stepping into nothingness. This altered state allows us to explore the depths of our consciousness and reflect on the unstructured aspect of our mind, shedding light on the nature of existence and absence. Meditation, on the other hand, is a discipline that intentionally guides individuals towards states of stillness and mindfulness. As practitioners quiet their thoughts and sensations, they can cultivate an experience that resembles nothingness. In these moments of profound calm, feelings of separation from the self and the external world can emerge, leading to a sensation of merging with the void. This state invites practitioners to let go of attachments, desires, and distractions, emphasizing the intrinsic peace that can be found in the absence of thought and the chaos of daily life. Both dreams and meditation can reveal that nothingness is not simply an absence, but also a rich landscape for exploration. These experiences can challenge preconceived notions about presence and absence, inviting deeper connections with our emotions, thoughts, and even the universe itself. In dreams, one might confront fears or unresolved issues, using the lack of structure to understand personal narratives better. Similarly, in meditation, the stillness often leads to profound revelations, expanding one's perspective beyond the usual confines of the mind. Engaging with nothingness through these states cultivates awareness, encourages introspection, and ultimately enhances our understanding of existence. Dreams and meditation become gateways to exploring the vast domains of consciousness, where experiences of emptiness can foster clarity and insight into the interplay between being and non-being. As individuals navigate these dimensions, they may discover that nothingness holds immense potential for growth, understanding, and appreciation of the intricate tapestry of life. Different scientific disciplines approach the visualization of nothingness in fascinating and varied ways, each offering unique perspectives informed by their methodologies and focus areas. In physics, especially in the context of quantum mechanics, scientists grapple with concepts such as a vacuum of space, which is often portrayed as an empty void. However, physicists illustrate that this void is not truly empty. It is a seething mass of energy and particles that pop in and out of existence. Visualizations, often using complex mathematical models, depict fluctuations in energy that challenge traditional views of nothingness, transforming it into an active and dynamic field. In cosmology, scientists delve into the vastness of space, attempting to visualize the cosmic background radiation that permeates the universe. This radiation serves as a remnant of the Big Bang and is a fascinating example of how something can emerge from a state that might seem like nothing. By employing detailed simulations and images of a universe's evolution, cosmologists present a view of nothingness that is rich with potential. These visualizations are vital for comprehending how the universe developed from an initial state of extremely high density and temperature to the expansive cosmos we observe today. Philosophy of science also intersects with these discussions, as philosophers reflect on the implications of scientific findings related to nothingness. They often propose thought experiments intended to stretch our understanding of absence. Visual tools used in philosophical inquiries might include diagrams or conceptual models that seek to bridge the gap between abstract theories and tangible experiences. Such visualizations encourage deeper reflection on the nature of existence and what it means to consider something as devoid of being. In the field of psychology, visualization techniques are utilized in therapy to explore the concept of emptiness or void within an individual's mental landscape. Therapists may guide clients in visualizing feelings of nothingness as a way to process emotions or confront anxieties. Through these techniques, nothingness is rendered into a more relatable and tangible experience, facilitating introspection and healing. The intersection of these disciplines highlights that, while nothingness may initially seem abstract, there are myriad ways of visualizing and understanding it that speak to both scientific inquiry and human experience. The Big Bounce is a theoretical cosmological model that posits a cyclical nature of the universe, suggesting that instead of a singular beginning, the current universe is a result of contraction of a previous universe, followed by a subsequent expansion. This contrasts sharply with the traditional Big Bang theory, which describes a singular event approximately 13.8 billion years ago when the universe rapidly expanded from an extremely dense and hot state. The Big Bounce introduces the idea that the universe undergoes periodic expansions and contractions, implying that it may have existed in different forms infinitely in the past and will continue to do so in the future. One of the central challenges the Big Bounce presents to the Big Bang theory is its approach to addressing the origins of the universe. The Big Bang theory leaves questions about what occurred before the singular event, as time itself is thought to have begun with the expansion. In contrast, the Big Bounce offers a more dynamic history, suggesting that the universe's expansion follows contraction phase. This notion helps to circumvent some of the philosophical and scientific dilemmas regarding the absolute beginning of everything, proposing a universe that is eternally cycling through phases of collapse and rebirth. Additionally, the Big Bounce is informed by developments in quantum gravity and string theory. These areas of theoretical physics attempt to reconcile the principles of general relativity, which governs large-scale structures, with quantum mechanics, which rules the microscopic world. According to some models, including loop quantum gravity, the collapsing universe reaches an incredibly high density before undergoing a bounce, leading to a new phase of expansion. This alteration in paradigm could offer insights into phenomena observed at cosmic scales, addressing questions related to the fate of the universe and the singularities predicted by the classical Big Bang model. The concept of the Big Bounce continues to inspire debate and research within cosmology, challenging fully accepted understandings of the universe's inception and evolution. It invites scientists to reconsider the implications of current models while exploring the myriad possibilities for the universe's past and future. This ongoing investigation reflects the dynamic nature of scientific inquiry, illustrating how new theories can reshape our understanding of fundamental questions about existence itself. The theory of eternal inflation offers a compelling framework for understanding the state preceding our universe. According to this model, the universe experienced a rapid expansion called inflation, which occurred just after Big Bang. However, unlike traditional models that suggest a singular event, eternal inflation posits that this inflationary process is ongoing in different regions of a vast multiverse. In this scenario, while our local universe underwent a tremendous expansion that cooled and settled into the cosmos we observe today, other regions continuously inflate, creating a tapestry of universes, each with potentially different physical laws and constants. At its core, eternal inflation suggests that the very fabric of space-time is eternally undergoing fluctuations, resulting in bubbles of space where inflation ceases and traditional cosmic evolution occurs, like the formation of galaxies and stars. Our universe is just one of countless bubbles that have formed from this persistent inflationary process. Before our universe took shape, conditions were dominated by a chaotic state characterized by rapid expansion and high energy densities, with quantum fluctuations giving rise to the seeds of structures seen today. One of the most intriguing implications of eternal inflation is that it may offer solution to some of the unresolved questions of cosmology, particularly about the initial conditions of our universe. This theory implies that the pre-universe state is not necessarily a singular point, but rather a complex landscape filled with potential. Within this context, causality is extended beyond our observable universe, as events happening in distant inflating regions may influence the cosmic background in subtle ways. Eternal inflation also introduces the idea of a multiverse, where each bubble, including our universe, might have different characteristics. This possibility prompts philosophical inquiries about the nature of existence and the very concept of our universe as just one manifestation among many. Overall, the theory of eternal inflation redefines how we perceive the beginnings of our universe by placing it within a much larger, ever-evolving context that continues to spark scientific curiosity and inquiry. The no-boundary proposal, introduced by the renowned physicist Stephen Hawking and his colleague Jim Hartle, presents a fascinating perspective on the origins of the universe. This model seeks to address the question of what happened at the very beginning of the cosmos by proposing that the universe does not have any boundaries, either in space or time. According to this idea, the universe can be thought of as the surface of a sphere, where the concept of before the Big Bang becomes meaningless, as time itself does not have a defined starting point in the traditional sense. The essence of the no-boundary proposal lies in the notion that the universe emerged from a quantum state devoid of classical properties. In this framework, instead of starting from a singularity, an infinitely dense point, Hawking and Hartle suggest that the universe began in a smooth, finite state. This state is characterized by a no-boundary condition, where the laws of physics as we understand them break down. The proposal employs the principles of quantum mechanics combined with general relativity, showcasing that the beginnings of the universe can be described using the mathematics of complex geometrical structures known as Wheeler-DeWitt equations. In practical terms, the no-boundary proposal implies that while we can observe and measure our universe, its initial conditions were shaped by quantum fluctuations that yield an infinite diversity of possible outcomes. The universe's history unfolds from this initial state, smoothing out as it expands and evolves according to physical laws. By reconceptualizing the universe in this manner, the model suggests a way to sidestep complicated questions about what preceded the Big Bang and how time functions at the very edge of the cosmos. This groundbreaking theory has significant implications for how we understand our universe's origin and structure. It invites a rethinking of classical notions about space and time, suggesting that rather than starting from a chaotic singularity, the universe blossoms from a quantum landscape where boundaries and origins blur. The no-boundary proposal continues to influence both cosmological research and philosophical inquiry surrounding the nature of existence, showcasing the innovative spirit of modern theoretical physics. String theory offers a unique and complex framework for understanding the pre-Big Bang state of the universe by suggesting that the fundamental building blocks of reality are not point-like particles, but rather one-dimensional objects called strings. According to string theory, these strings vibrate at different frequencies, giving rise to the various particles and forces observed in nature. This theoretical structure has profound implications for cosmology and the exploration of the universe's origins. In the context of pre-Big Bang scenarios, string theory posits that our universe may be just one of many within a larger multidimensional space known as a bulk. Before the onset of what we recognize as a Big Bang, string theory allows for a framework where strings could have existed in a different state. Some models suggest that before the Big Bang, the universe could have been in a highly energetic and dense condition, often referred to as a string gas state, where numerous strings interacted in complex ways. This state could lead to the emergence of our universe as one bubble among many, formed from vibrational modes of strings settling into a more stable configuration. Furthermore, string theory incorporates concepts like brain world scenarios, where our universe is a three-dimensional brain embedded in a higher dimensional space. In this model, events on the brain, including the Big Bang, could have been triggered by collisions with other brains or interactions within the bulk. Such collisions could provide the necessary energy for our universe to expand, creating a dramatic transition from a pre-Big Bang state into the universe we currently inhabit. String theory thus challenges conventional understandings of cosmology by suggesting that the Big Bang may not be a singular, definitive beginning, but rather part of a continuous cycle of interactions among strings and brains in a higher dimensional space. This perspective encourages a re-evaluation of what we consider the origins of the universe, positioning the Big Bang as a transition from a prior state defined by string dynamics. Although still largely theoretical and mathematically intricate, string theory expands the horizons of cosmological inquiry, leading to exciting possibilities regarding the nature of existence both before and after the Big Bang. The cyclic model of the universe, proposed by physicists Paul Stenhardt and Neil Turok, present a fascinating alternative to traditional cosmological models that posit a singular beginning. According to this innovative theory, the universe undergoes an eternal sequence of expansions and contractions, with each cycle consisting of a Big Bang-like phase followed by gradual expansion, ultimately leading to another contraction and the next Big Bang. This model emphasizes that, rather than being a one-time event, our universe is part of an ongoing cycle of rebirth, presenting a dynamic perspective on cosmic evolution. At the heart of the cyclic model is the idea that the universe consists of higher dimensional brains, influenced by ideas from string theory. In this framework, our three-dimensional universe is viewed as a brain that periodically collides with another brain, triggering a bounce or a new phase of expansion. Each collision results in a dramatic release of energy, akin to a Big Bang, initiating a new cycle. The key component of this model is that these interactions can continue indefinitely, allowing for a universe that is ageless and continually evolving. One significant advantage of the cyclic model is its capacity to address some of the unresolved questions posed by traditional cosmological theories, including the apparent fine-tuning of the universe and its current accelerating expansion. By incorporating elements from the realms of quantum physics and cosmology, Steinhardt and Turok provide a mechanism for resolving such issues through the dynamics of the cyclic process. For example, the processes occurring during the contraction phase can help smooth out irregularities and set the stage for fresh cycles, imparting a sense of self-regulation to the universe's evolution. The implications of the cyclic model extend beyond cosmology to also engage with philosophical questions regarding time and existence. By suggesting that the universe experiences an infinite series of cycles, this theory proposes a view of cosmic history that transcends conventional narratives tied to singular beginnings. Although the idea remains under scientific scrutiny, it opens intriguing avenues for inquiry into the nature of time, the origins of our universe, and how physical laws might govern the grand cyclical dance of creation and destruction on a cosmic scale. Loop quantum cosmology offers a distinctive perspective on the state preceding the Big Bang by applying principles derived from loop quantum gravity, a theoretical framework that seeks to unify general relativity and quantum mechanics. This approach fundamentally alters our understanding of the universe's beginnings, suggesting that the structure of space-time itself features discrete, quantized properties rather than being a continuous entity. In this view, the universe may have undergone a significant transition, rather than a singular beginning at the Big Bang. Prior to the Big Bang, loop quantum cosmology posits that the universe was in a highly dense state, characterized by quantum fluctuations. As the universe approached this critical state, it transitioned through what is termed a quantum bounce. Instead of encountering a singularity where density becomes infinite and the usual laws of physics break down, the framework suggests that the universe contracts and then rebounds. In this model, gravity plays a crucial role, as a quantization of space-time prevents the formation of singularities that plague traditional cosmological models. The implications of this approach are profound. Instead of the Big Bang serving as the absolute beginning of time and space, loop quantum cosmology allows for the idea that the universe may have existed in a prior state, characterized by contraction. The bounce then represents a transition into the expansion we currently observe. This model helps resolve some of the philosophical dilemmas surrounding the nature of time, as it implies that time can extend beyond the Big Bang, and that new cycles of expansion could potentially emerge from earlier collapses. Loop quantum cosmology not only addresses the challenging issues of singularities, but also provides a framework for analyzing the early universe's dynamics. By emphasizing the quantum nature of space-time, this approach enables scientists to explore how the universe evolved through various phases, potentially leading to new insights about its overall structure and longevity. This exciting avenue in theoretical physics continues to inspire research and debate, offering a captivating look at the fundamental nature of our universe and the events that shaped its origins. The ekpyrotic universe theory presents a novel cosmological model that directly challenges conventional understandings of the Big Bang. This theory, introduced by theorists including Paul Steinhardt and Neil Turok, posits that the universe's evolution originated from collision of two three-dimensional branes in a higher dimensional space. Rather than envisioning the Big Bang as a singular explosive event, the ekpyrotic suggests that our universe was birthed from the energy and dynamics of this collision, marking a transition from a prior state defined by the interactions between these branes. In this context, the pre-Big Bang state is characterized not by nothingness or singularity, but by a preceding existence of physical structures and energy within the higher dimensional space. Before the collision, the branes could have been in close proximity, with their dynamics influencing the fabric of space-time in ways that would impact what we observe in our universe today. The collision itself generates the hot, dense conditions that align with characteristics expected of the early universe, effectively showing how our Big Bang is a natural outcome of these interactions, rather than a unique and isolated event. One key feature of the ekpyrotic model is its ability to mitigate some of the issues associated with traditional Big Bang theory, including the flatness and horizon problems. By emphasizing more gradual transition from one state to another, the theory offers an alternative mechanism for structure formation, suggesting that density fluctuations can arise from quantum perturbations occurring in the pre-collision environment. This shifts the focus from explosive expansion to a more nuanced understanding of the cosmos, where interactions in higher dimensions lay the groundwork for the observable universe. The ekpyrotic universe theory emphasizes a cyclical nature reminiscent of other cyclic models, as it allows for the possibility of multiple collisions and consequently multiple universes. This vision reshapes not just our understanding of cosmic origins, but also the nature of existence itself, prompting thought on how interconnected forces in higher dimensions may govern the boundaries of our own universe. Ultimately, the ekpyrotic model encourages a fresh perspective on the pre-Big Bang state by integrating ideas from string theory and brane cosmology, blending them into a cohesive framework that expands our comprehension of the cosmos. The concept of a multiverse introduces the idea that our universe may be just one of many universes, existing simultaneously in a vast, interconnected framework. This notion can significantly reshape our understanding of what might have existed before our universe, providing a broader context for exploring cosmological origins. Several theoretical frameworks, such as inflationary cosmology, string theory, and the ekpyrotic model, propose different forms of multiverse, each with unique implications for pre-Big Bang states. In the context of inflationary cosmology, the multiverse arises from the idea that different regions of space can undergo inflation at different rates, leading to pocket or bubble universes. Each bubble corresponds to distinct physical characteristics, potentially governed by different laws of physics. Before our universe came into being, it might have originated from an inflating field that decayed, producing a particular bubble while leaving vast stretches of inflating space around it. This infinite sea of inflation could imply that numerous other universes exist, some similar to ours and others radically different, each emerging from their unique conditions and quantum fluctuations. In string theory, the multiverse concept can manifest through different configurations of branes and dimensions. The interactions between these branes could give rise to various universes, each encapsulating different physical properties. The pre-Big Bang state, therefore, may not simply precede our universe, but exists amid an expanse of other cosmos, all intertwined yet separate. This would suggest that existence extends beyond our comprehension, incorporating myriad forms of reality that defy conventional boundaries. Moreover, the ekpyrotic model also supports the multiverse hypothesis, as it envisions a universe born from a collision of branes in higher dimensions. Each of these collisions can lead to the formation of diverse universes, creating a scenario where what we consider to be the singular Big Bang is merely a localized event within a broader multiverse structure. The idea of a multiverse encourages a rethinking of traditional cosmological narratives, as it presents multiple avenues for understanding both the origins of our universe and the nature of existence itself. While challenging to empirically test, the multiverse concept invites deeper philosophical reflections on reality, prompting us to consider the boundaries between universes, the nature of time and space, and what it truly means to exist within an ever-expanding cosmos of possibilities. Conformal cyclic cosmology, proposed by renowned physicist Roger Penrose, presents a compelling alternative perspective on the universe's evolution and the nature of cosmic time. This theory suggests that the universe undergoes an infinite series of cycles, where each cycle is referred to as an eon. Unlike traditional models that view the Big Bang as a singular event marking the universe's beginning, conformal cyclic cosmology posits that each eon evolved from the remnants of the previous one, facilitating continuous process of rebirth. The key to understanding this model lies in the concept of conformality. Penrose argues that, as the universe ages and expands, its structure becomes increasingly simpler, with matter and energy dissipating and rendering it closer to a uniform state. In this highly expanded, low-energy condition, the distinct properties of time and space begin to lose their traditional meaning. Penrose asserts that, at this juncture, the universe can be mathematically transformed into a new eon through a process of conformal mapping. This transformation blends the end of one eon seamlessly into the beginning of another, maintaining the fundamental structure of space-time while erasing the features that distinguish previous cycles. This framework allows for a universe that is eternal and evolves without requiring a singular origin point, as traditionally defined. It emphasizes that the Big Bang is not an absolute beginning, but rather a transitional phase that arises from the end stages of a prior universe. The transition between eons can be seen as a smooth fading out of complexity, where the remnants of previous cosmic structures contribute to the new cycle without retaining any memory or distinct characteristics. Penrose's conformal cyclic cosmology offers compelling insights into questions about the nature of time, existence, and the fate of the universe. While the theory remained controversial and subject to debate within the scientific community, it provides a novel view that challenges conventional narratives, suggesting that the universe is engaged in an endless dance of cycles, each one leading to the next, blurring the lines between beginnings and ends. By encouraging fresh perspectives on cosmology, Penrose's model fosters profound inquiries into the nature of reality itself and our understanding of the cosmos across infinite scales of time. The chaotic inflation theory presents a fascinating perspective on the state of our universe prior to what we can currently observe. According to this theory, before the Big Bang and the subsequent expansion that led to our observable universe, there existed a vast expanse of space filled with energy undergoing rapid fluctuations. This realm was characterized by an inflationary phase that could have begun in a multitude of ways, leading to different pockets of inflation, each potentially developing into separate universes or bubbles. In this scenario, the chaotic inflation theory suggests that the conditions were not uniform. Instead, variation in energy density created regions that inflated at different rates. This means that, while one region might have transitioned into the familiar universe we inhabit, nearby areas may not have experienced the same fate, resulting in an incredibly diverse multiverse. Each of these universes could feature unique physical laws and constants, highlighting the randomness of cosmic processes. Surprisingly, the universe we observe now, with its galaxies, stars, and planets, is only a small part of a far larger and more complex reality. The chaotic inflation theory encourages us to reconsider our place in the cosmos, as it implies that our universe is simply one manifestation in a potentially infinite expanse of diverse realities. This idea of multiple universes challenges our understanding and evokes profound questions about the nature of existence itself. Through chaotic inflation, we gain insights into the early moments before our universe took shape, emphasizing the chaotic and unpredictable forces that shape the cosmos. This theory not only deepens our understanding of cosmic evolution, but also invites us to ponder the mystery of what lies beyond the limits of our observable universe, sparking curiosity about the nature of reality itself. The notion of time before the Big Bang is one of the most compelling and perplexing puzzles in cosmology. According to the standard model of the Big Bang theory, time and space originated simultaneously at the moment of the Big Bang, approximately 13.8 billion years ago. This suggests that asking what happened before this event may be fundamentally flawed, as time, as we understand it, did not exist prior to the Big Bang. Essentially, the Big Bang marks the beginning of time itself. Some physicists theorize the existence of a timeless state or a phase where traditional concepts of time are not applicable. In such a scenario, events as we know them could not take place because the very framework of temporal progression was absent. Discussions surrounding this period often lead to the exploration of alternative timelines or conditions of existence where the rules that govern our universe might not have applied. Other theories explore the potential for a cyclic universe, where the universe undergoes endless expansions and contractions. Under this model, the Big Bang does not mark a definitive beginning, but rather a transitional point in a continuous cycle of creation and destruction. This perspective opens the door for meaningful discussions about events that could precede our current universe. Although these ideas remain speculative and challenging to verify, these explorations push the boundaries of our understanding, inviting us to consider the limits of scientific inquiry. The quest to make sense of the time before the Big Bang underscores humanity's deep-seated desire to comprehend not only the origins of the universe, but also the fundamental nature of reality itself. It poses profound philosophical questions about existence, the flow of time, and what before could even mean in a context where time itself did not exist. As we approach the Big Bang singularity, our conventional understanding of time begins to break down in remarkable and challenging ways. At this singularity, equations of physics, particularly those outlined in general relativity, reach a point where the curvature of space-time becomes infinitely steep. This suggests a situation where the laws that govern the fabric of the universe cease to function as we expect, rendering our traditional notion of time effectively meaningless. Near the Big Bang, the density and temperature of the universe were extraordinarily high, creating extreme conditions. In this environment, time as we know it, a linear progression of past, present, and future, is no longer a reliable measure. Instead, all events seem to converge into a point where our usual chronological framework collapses. Thus, Trying to apply the standard rules of time leads us into a realm of paradox and confusion, where notions such as before and after lack clear definitions. This breakdown of time highlights the limitations of our current scientific understanding. While quantum mechanics offers insights into the behavior of particles at incredibly small scales, it has not yet been reconciled with the expansive framework of general relativity. Approaches such as quantum gravity aim to bridge this gap, offering potential pathways to understand how time and space might behave at the singularity. However, these theories remain in the realm of theoretical physics and continue to provoke further questions. The implications of this breakdown challenge our very conception of reality, compelling us to reconsider fundamental aspects of existence. They encourage thinkers and scientists alike to venture beyond traditional boundaries, exploring not just what came before the Big Bang, but what it truly means to experience time and space in a universe marked by such extraordinary beginnings. The pursuit of understanding time's role in the cosmos ultimately enriches our appreciation for the intricate nature of reality itself, drawing us into the depths of the mystery that lies beyond our current knowledge.